Good morning, everybody, and thank you very much for joining us today for this webinar on AI for discovery, in which we're specifically going to be taking a technical deep dive appropriate for researchers, librarians, and publishers. What I'd like to cover in terms of the agenda is, first of all, why AI is relevant in the discovery sphere. We're going to look at the challenge of information overload, fragmented sources, and how people can formulate a good search query. Then we're going to look specifically at graph data science and knowledge graphs. And why is a knowledge graph really appropriate? So a knowledge graph is an appropriate technology when relationships matter. So if there are no relationships in the things that you're trying to research or curate, you probably don't need them, but odds on there are. Then I'm going to take you through some very specific examples of taking a piece of text and how that can be converted into something that can be read by a machine and included in a knowledge graph for discovery. And then we'll look at a range of different formats and different types of information. And then we'll conclude really looking at the key questions you should ask if you're thinking about implementing some kind of AI technology. So there will be an opportunity at the end to ask questions, and at any time, do feel free to send in questions over the chat and the QA function. So first of all, to frame the problem, I think we're all overwhelmed every day by the information that we receive. And to put it into context, it will take over 3,000 years for a team of 10,000 analysts to read all of the unstructured information currently available today. And when we think about information, we're very often thinking about published information, but there's a huge amount of information in corporations, in personal storage. So actually being able to put all of that together and derive something is, in this order of magnitude. And in terms of looking at that challenge in a different way, as you look at all of these different data sources, if you are a researcher, what you're looking to do is find what you're looking for. So you're being overwhelmed by all of these different sources being presented to you. You have to work out the high quality ones. And then once you do find that, you have to find the exact section of the text you're looking for. If you're an owner or if you license content, you want that to be found easily by your community. And you also want it all to be able to remain up to date in terms of the search terms and the language that it uses. And if you create content, you want it to be discoverable across all the range of different environments and different platforms. So we're going to cover some of those challenges today and how AI can help in some of those situations. And I think in terms of looking at knowledge graphs, the reason for looking at that technology specifically is because it's not just about finding content or discovering documents. It's also about giving researchers context, and it's also about helping people find the exact section of text that they're looking for. So before I move into the deep dive specifically in the technology, I wanted to share this with you. So what you're looking at here, and as you see these lines move, this is an extract from a knowledge graph, and it's looking at news data that was being ingested from January 2020, about 10,000 items a day. And what's happening, as you can see, is these lines all represent different companies. And as news is being ingested, the relationships between the companies, the importance of what's going on is changing. And so this is really to highlight the point that actually when you are looking at information and content, you need a dynamic environment, because as new content is produced, the relationships between items, between concepts will change. Some things will become more or less relevant, and so on and so forth. And I'm showing you this really looking at news. Obviously, there's way more than 10,000 items of content a day produced, but news is a really good source, because you can imagine in real time, all of us are busy trying to read newspapers. And of course, we can't even keep up with this, let alone all the other sources. So hopefully this gives a sense of how information is moving in real time and how it can be stored in a knowledge graph to understand the relationships and to actually derive some intelligence. So that's all I was going to say in terms of an introduction. But what I'd like now is to move into a much more detailed section, looking at specifically knowledge graph technology, how it works, and how artificial intelligence can provide a dynamic environment for discovery. So first of all, looking at how you can take unstructured text and turn it into something that can be read by a knowledge graph or AI technology. So what you can see in this slide, on the left-hand side, you have content. It can be any kind of unstructured content. So it could be something like news, as we saw on the previous slide. It could be books, journal articles, patents, clinical trials, dissertations, reports, internal government documents, any kind of unstructured text, and it could be any range of different lengths, from a paragraph of text, a few sentences of text, to hundreds or thousands of pages of text. And so what you see happening in the middle is that that text is ingested and a series of algorithms are run over the text. And what the algorithms are trying to do is to recreate the way that a human would read the text. So they're trying to recreate a neural network model. So as the algorithms are reading the text, they're not simply hunting for keywords. They're actually understanding what is being said. So they're able to disambiguate, they're able to understand context, and they're able to identify meaning in the form of concepts. And as they identify a concept, that concept is extracted, it's promoted, and it's projected onto the right-hand side where you see a knowledge graph. And so the knowledge graph is a multidimensional semantic vector space. And referring back to the previous slide where you saw the bars move, this is not a static environment. This is a real live dynamic environment. So it's moving. So within the knowledge graph, you have concepts and connections, and those relationships can change over time. So new relationships can be formed, relationships can strengthen, weaken, and so on and so forth. So that knowledge graph is really very dynamic, and it will change as new content is ingested and new things become more or less important. So that's a snapshot of the end-to-end process by which you can take any kind of unstructured text and turn it into a mathematical formula that can be read by technology and create a knowledge graph. And then, of course, looking at the knowledge graph in that form isn't usable to a human, but you will then use that information. And one of the reasons for using graph technology is that a mathematical graph is a fantastically flexible instrument. So many different people can use it in different ways to extract the information that they're interested in using. But the key thing is that it's continuously up to date. So now looking a little bit at the concept-based approach, I talked a little bit about the algorithms reading the text and identifying meaning and extracting that in the form of concepts. So a concept can be a word or a group of words, but the key thing about it is that it has to have a definition. And we'll come onto that in a couple of slides. And so concepts all carry with them a kind of significance and an inference. And by inference, I mean a connection. And a connection can be inferential or direct. So when you look at a direct connection, that's where you would have a piece of text, it would mention two things, and you can see that those two items are clearly directly connected. And inferences are where algorithms or a human brain can identify that there is probably a connection between two things where it hasn't been explicitly stated. So what is a concept? The important thing about a concept is that it's an atomic unit of information, and it will always have at least one definition. It may have multiple definitions, and it can pertain to one or more topics. So if we look at this example here, you've got a picture of Jaguar the animal on the left, and we have a definition there. So we understand that the jaguar is the largest cat in the Americas with a compact body, a broad head and powerful jaws, etc. And then we can look on the right-hand side, and exactly the same word is used for Jaguar, the luxury vehicle brand of Jaguar Land Rover, a British multinational car manufacturer. And then if you look underneath those two things, both of them have been assigned different topics and subtopics. So we see Jaguar the car in the topic of engineering and the subtopic of car. And then we see it also in marketing and brands. And when we look at Jaguar the cat, it's in the topic of nature with the subtopic of zoology, and also again, the topic of nature, but a subtopic of wildlife. So the key thing is that as an algorithm is reading a piece of text and it sees the word Jaguar, it understands, due to the surrounding context, if it's talking about a car or a cat. And we'll come on to some more examples of disambiguation and how important that is later on. So exactly how are new concepts extracted? So what you can see here on the left-hand side is a piece of text from a document, and highlighted in purple in the text is the words monetary policy 3 times. So as the algorithms are reading the text and they're identifying monetary policy as a potential candidate, it then gets extracted and promoted. And having been promoted, the next thing you need to know is a definition. So a description lookup tries to find automatically a definition for that concept. And all of this is an unsupervised machine learning process. It's not actually a person doing it. And then it finds this definition, So monetary policy is the process by which the monetary authority of a country controls the supply of money, often targeting an inflation rate or interest rate to ensure price stability and general trust in the currency. So that now becomes a concept because it is two words plus a definition, and the context is also understood. So where that concept is found, it can be added into the knowledge graph, and it can be sensibly connected to other items in that graph, and it can change over time as new content is added. I always get asked about NLP versus computational linguistics. So I have a couple of slides here to talk a little bit about the differences. So when you talk about artificial intelligence, you're talking about a huge range of terms, anything from NLP to robotics, etc. And NLP is definitely part of the world of AI. It started off in about 1970, and it was a huge leap forward in terms of being able to extract keywords from text. But it's all about statistics. It's not actually understanding the meaning of the text or the context of the text. It's all about hunting for keywords. So distributional hypothesis is where we're looking for words with similar meanings occurring in similar context. And there's a correlation between the distributional similarity and the meaning similarity. So that is not a bad approach, and it's definitely helped us over the past few decades. But the two challenges you face when you use that approach alone are that you can have this coexistence of many possible meanings for a word. So we looked at the example of Jaguar. Another one we'll come on to is Java, which could be so many different things, from a programming language to an island to a coffee. And then you also have synonymy. So you have different terms with equivalent meanings. So really, in order to be able to provide a really, really great discovery environment, you need to take the meaning of the concepts into account, not just their relative position, their count, etc. And that's why you need the semantic space. So looking at how it works, so where distributional hypothesis is a rule-based approach operating at a keyword level, and it's not able to take into account these multiple meanings for the same word or ambiguous concepts, the semantic space, which you see in a knowledge graph, and there's a tiny example on the right of an extract from a knowledge graph, is able to do this. So what's happening is we can see apple, the same word. So if it was a keyword, you'd just have apple, but where it's a concept, we're able to identify apple, a company, which you see as an orange concept, and apple, the fruit. And what we're trying to show with the arrows is different vectors in a multidimensional semantic vector space. So apple, the company, has been projected into the vector with other software companies like Microsoft and things like Java, the programming language. Whereas apple, the fruit, has been projected into a completely different plane of this vector space next to another fruit called pear. We can also see Java, the programming language, which is close to apple, the company, and Microsoft in one plane of the vector space, where Java, the island, is in a different plane next to Indonesia. So hopefully that gives some sense of how NLP can contribute, but isn't a comprehensive solution in terms of not actually being able to understand the context. So I wanted to talk a little bit about disambiguation, because if you own content, or if you're a researcher trying to find content, you always want to be able to disambiguate in order to find what you're looking for. So to give an example of a great term, so if somebody's researching for depression and they go to a search bar and put in the word depression, they could be talking about geology, they could be talking about a low pressure area in meteorology, they could be talking about an economic depression. They might also be thinking about the Great Depression, the Long Depression, or the Depression of 2021. They could be thinking about depression in the mood, depression in physiology, or a major depressive disorder. And these are just some of the variations. I could go on for several more slides on depression alone, but I think hopefully that captures the importance. So when you're looking to search for something, the keyword alone is not enough in terms of the search term. You need to be able to disambiguate that term to take people to the right kind of things that they're looking for. Another really important thing that AI can help with is really about this understanding of context and meaning. There's so much content going back decades, hundreds, and even thousands of years. And actually the term that we use today may well not be the term that somebody has used in the past. And equally, it can change in the future. So what you've got in front of you is a couple of examples of snippets of text that are talking about 3D printing, but the term 3D printing isn't actually mentioned in the text itself. So the great thing is that algorithms are able to read through this huge amount of content and understand that maybe something that was written 15 or 25 years ago didn't talk about 3D printing, but they can understand when it's the different words are actually describing the same thing. Because the algorithms are understanding the meaning, they're understanding what is being written about, and they're understanding the context. So you're able to surface parts of documents where the current term that we use today was not in use previously. And the other thing about concepts versus keywords is that language will evolve. So if I take you through a couple of examples, the word Brexit was coined in about 2016 in the media and started being used broadly, but it wasn't actually a new thing. The idea of Brexit, I think the origins go back to 1964, and it actually means the United Kingdom withdrawal from the European Union. So if somebody is searching through your content or using a search bar, they might put in Brexit, they might put the United Kingdom withdrawal from the European Union. In either circumstance, they should be getting the same comprehensive results. Looking at a different example in science, I'm English and there's a drug that I used to take when I lived in the UK called Nurofen. Nurofen is a brand name. And actually, if somebody is searching for that, they might want to know actually that it's called ibuprofen, or I think in the US, ibuprofen. So it's very important that you don't think that you're getting all of the information around something where in fact you've used a specific term and it's given you a specific narrow angle on that. You definitely want to understand where a term could be using a different word, and then you want to get all of the research that's relevant, not just those that are relevant to the term you're using, when in fact there are many, many other things that mean the same. And terms change over time. So the key thing is that because a concept is attached to a definition, if the word someone uses is a different word, but the meaning is the same, they'll still be able to find it. So particularly important in science where drug names and things do change so much over time. So that takes us through to the end of the technical. And now what I wanted to do, explain really how this happens, how you can go from a raw piece of unstructured text into this very rich world of concepts, which are given huge amounts of granularity and helping discovery. So what we're going to talk through here is on the left-hand side, we've got a piece of unstructured raw text that can be ingested into a pipeline. Then the first thing that we do in a pipeline is we start by splitting the piece of text into snippets. And there are many reasons for this. And at the end of the day, one of the most important things is that a researcher wants to go back to the exact section of text that's relevant to them. So if, for example, you find a book and you've identified that that book is relevant to your research, but it's 400 pages, you're not going to want to read all of those 400 pages to find this section that is relevant to you. Equally, you might do a search in a traditional environment, get a very long list, and as you go through the items, they're not actually exactly what you were after. So if a researcher can be taken to the exact section of the text that is relevant or pertinent to their search query, and they can read that paragraph, at that point, they'll understand whether it is in fact what they're looking for. And if they choose, they might want to read the full journal article, the full book chapter, or even the full book itself. But they will want to go to that very section because no one's really got time to read through the entire contents to identify if it is or isn't relevant anymore. Once you've divided the item of text into snippets, you will perform the concept extraction. And for each concept, you'll compute different metrics. So it'll give different pertinence metrics and all kinds of different things, enable you to position it correctly into the knowledge graph and relate it to other concepts. So you can see here a tiny section of text, while other asset classes don't like increased volatility and so on. And from that, a couple of concepts have been extracted. We can see cash flows and dividends. And as you can see beneath that, you see these two concepts that have been extracted. They have a concept ID, the concept has a name, and it has a pertinence score. And that's giving you a sense of how relevant that concept is in that item of text. And in the bigger knowledge graph environment, you can of course relate concepts to other concepts from different items of text. So now looking at the entire section of text, and this is a news article. So you can see at the top, we've got 8 lines of news. And then what you can see underneath is the concepts that have been extracted. So they're very broad. They're everything from the Great Recession to precious metal, investor, asset allocation, Chicago Board Options Exchange, and each of those concepts has a definition. And as you can see here, they all have a score, a pertinence score. So you can tell how relevant they are in relation to that article. And then when you project them into a knowledge graph, you can have the relationships with other items correct in terms of their pertinence to those things. So hopefully that gives a kind of overall snapshot of how you can take a piece of raw text and convert it through technology and extract all of these concepts, which can then be related to all the other concepts. And I'm now going to look at some very specific examples of text and how this works. So I often get asked about different types of text. So I wanted to cover here a broad range of different types and lengths. So I'm going to start off with a journal abstract. So you can see here a journal abstract, and from this, 10 items have been extracted. There's a huge variation when you look at metadata in terms of the semantic metadata that is available. It can be anything from 0 keywords per item to, I think on average, about 3 to 8, occasionally more. And again, there's a complete variation in terms of how those keywords are assigned. They could be author assigned, they could be editor assigned, they could be assigned from a predetermined vocabulary, and so on and so forth. So one of the great things about using some kind of artificial intelligence technology is around consistency. And the other thing is about the breadth of terms that can then be used. So if you look here, we've got 10 terms from an abstract, and an abstract, this is quite short, but on average, I would say a third to half a page. Then we've now got a full journal article. This is quite a short journal article, and I'm going to give you an example of a longer journal article on the next slide. So from a full journal article, the technology can extract 56 keywords, concepts, terms. So that's very rich. So that's really giving you a lot of information. And if you consider that somebody is interested in any of these terms, they can find the term, and then they can find the exact section of the text that they would be interested in. Looking at the next example, so this is a longer journal article, and from this, 121 terms have been extracted. And again, thinking about these 121 terms and thinking about the example at the beginning where we saw news and where we saw the lines moving, and we saw that all of those lines change position over the course of the days and weeks of January and February 2020 in terms of what they were showing. So if you think about traditional semantic metadata, if you only had 5 terms, something anywhere beyond number 5 in this list might be relevant tomorrow or in 2 weeks or in 2 months. But if it hasn't been identified and hasn't been extracted, the moment where it is relevant and the moment where the link between something else becomes important, it will never be surfaced because it hasn't been identified. So having a much longer list is incredibly useful, particularly when relating content to other types of content. Here is a magazine article, so slightly shorter, and again, it has 41 items. So again, fairly rich and way beyond a sort of traditional amount of semantic metadata. So this is very interesting. This was a machine translated academic interview. There's just a section on the right-hand side. So it was actually in a different language, then translated using Google Translate into English. And it was much, much longer. And it was about a specific piece of research looking at people's attitudes to religion. And they had quite a narrow group of terms that they were extracting. I think it was 4,000, and they were missing huge amounts of different terms. And so actually the ability of technology to identify a much, much larger, richer, broader set of terms gave incredible insights into actually what people were thinking in this specific series of interviews. And then finally looking at a book. So this actually goes on to 2 slides. And there are 776 keywords for this single book. And I think, that people have different reasons for being interested in AI and discovery. So if you're a publisher, you probably want your content to be discovered or surface better. You're possibly also interested in selling it. And there was an experiment that we ran with Stanford University Press, and we took a sample of books, and this was one of them, and adding all of the additional keywords. And we changed the subject headings. This book actually sold 7 times as many copies as it had done in the previous year. So if you enhance the semantic metadata in a certain way that people can find it, you can't make an item of content linked to the news or interesting if it's not, but it does offer that opportunity where it will be surfaced in many ways and many places where it hasn't previously been surfaced because the connections couldn't be made. So that's a final example in terms of the text that I wanted to cover. And then I just wanted to leave you with a few thoughts on the kind of key questions to ask if you're thinking about introducing AI or if you're interested in exploring it. And the first thing really is it a dynamic environment? Because content is always changing and the outside world is always changing, and being able to relate items of content to other connections, other things, understanding those relationships and making sure things are constantly up to date as language evolves and as terms evolve is really, really important. The next really important point to consider is, can the technology disambiguate? So we've looked at a lot of examples in this webinar. We've looked at the example of Jaguar, the car, the cat. We've looked at many different meanings of depression. We've looked at Java, the programming language, the island, the coffee. So there are so many terms like that that mean different things. And we need to use a technology that disambiguates so that a researcher, a user can find exactly what they're looking for when they're trying to discover content. The next really important thing to think about is context. So can the technology understand the context? So when you're looking at research, it's really, really important not to look in isolation, but to understand what's going on around what you're researching. And context is invaluable in that respect and very, very important to think about when you're thinking about how your content is found. So the fourth thing is really, does the system learn or does it need to be fed with keywords or concepts? So to distinguish, going back to the example about NLP, NLP is hunting for keywords. So it needs to be fed a series of terms, and then it will find those terms and it will use statistical distribution to identify similarity, relevance, etc. So what happens if that term set isn't comprehensive, or what happens when something new comes to the machine? It will be missed. So using neural networks and using artificial intelligence technology, machines can actually now learn. So they don't need to be fed a term, they will actually learn themselves. And it's really, really important that as you adopt a new technology, that you're using a technology that is able to do that. Otherwise, it will not be constantly up to date. And the final thing to think about is, do relationships matter? And are there connections and inferences? And personally, I think odds on there probably are for pretty much everyone on this call. So if that is the case, then something like a graph-based AI technology will probably be the most helpful. So hopefully that's covered what most people were looking to get from this call in terms of a deep dive into AI technology and how it can be useful or used in the discovery environment. But what I'll do now is I will go on to the QA and see what questions we've got. So do feel free to send in any questions you're interested to ask. So I'm just looking here in the questions to see what's coming in. So I have a question here. I can see how this technology would be directly relevant to librarians assisting researchers, but I'm struggling to understand how it can be applied. Can you talk about the front-end experience and how actually integrates with the search process for a library? Thank you very much for your question. Yes, so this is really to explain, and the purpose of the webinar is to explain the technology, but in terms of how it integrates, there are a couple of ways. So if you're interested in adding kind of Discover, which is our graph-based technology, into your library research tools, we do have what we call a widget, so it can be embedded in any of the existing search platforms, or if you have your own homegrown kind of blacklight. And what it does is adds context to search. So when a researcher goes to whatever search bar you currently have and they put in a term, then as the traditional list builds, you will also build a mini graph, and the graph can be positioned wherever you want it in terms of your existing environment. So it integrates with the existing environment and it offers a visual option versus a list-based option. So it's a complementary technology. But do feel free, if that didn't answer your question fully, do feel free to email in afterwards, and I can send you a picture. So then I've got another question here. How do we know whether the data can be disambiguated or not? So, I mean, interesting question. So I think in terms of any type of text, the first thing we always say to people is send a sample, because from our perspective and from the perspective of anyone who's using any kind of AI technology, you need to have high quality digitization. So we always check the samples. So if you have got some good digitized content, in terms of whether or not disambiguation can happen, then I would say yes for unstructured text, as long as you have a minimum length of a couple of sentences. There are words that don't have multiple meanings, but there are many that do have multiple meanings. So obviously a criteria is that it does have to be something that would have potentially multiple meanings. But I hope that answered your question. So the next question coming in, how many concepts do you have in your knowledge graph? So in our knowledge graph currently, we have over 5.5 million concepts, and that does continuously grow. Just reading through the questions. So next question, what subjects is this relevant for? So I would say you can use AI broadly for any kind of domain or any subject area. Very specifically, our philosophy was to create a kind of cross-domain approach. So, if a researcher comes into the platform and they don't necessarily know where they should go, they don't know whether, I'm doing a humanities search, I should go here, I'm doing a scientific search, I should go here. You don't have to know that, the relevant content will be surfaced for you. And we also think that great discovery in the future will come from the intersection of different domains of information. So it's very important to have all the different types of information in the same place. So I have another question here. Some users are interested in looking for specific items. They know the title of an article, a book, or a video. How does Yewno get those items without all the added information? That's a great question. And actually, we don't do that in Yewno Discover. We do that in a different product called Yewno Unearth. So in Yewno Discover, you cannot do known item searching. You cannot go in for by publisher or by title. If you want to do that, then we have a different product called Yewno Unearth, which allows you to search in that way. Then next question coming in. So another one on the types of content that is suitable. So any unstructured text is suitable. The only thing I would say is the limitation is on not having an incredibly short amount of text. So if you came along with a list, for example, like a shopping list. So when you give that to a machine, it cannot read a list of terms and understand any context because there is no context. So a list doesn't work. Also, if you had something, maybe a 4-word headline, that also doesn't work because it's not enough text for a machine to read to understand. So for example, we as humans can understand because maybe we're looking at a newspaper headline and we know what's going on around it. But if you gave a machine like 3 words without any of that, it wouldn't know. So it wouldn't be able to use a short amount of text like that. But broadly speaking, anything like a journal abstract, journal article, a dissertation, a book chapter, a patent, a report, anything like that is a suitable item of text. I've got another question here about collections. And this is an interesting question. I often get asked about knowledge graphs, and people with bespoke collections, maybe 400 items, maybe 70,000 items, are interested in creating a knowledge graph and having that knowledge graph visualization to help people find what they're looking for. So actually, in our knowledge graph, the first version we had 40 million items. So knowledge graph technology really is big data technology. So you do need a pretty big data set to start off with. And there's a number of sort of technical reasons for that. And the other thing about it is that when a researcher sees a search bar, even if you tell them, it's a very specific content set, they will put in something. And if they don't find results, then that's a pretty bad experience. So what I would say about content is that even if you have a very small content set, you can still, using AI technology, you can still go through the process for ingestion and concept extraction and get incredibly rich semantic metadata. And you can also take any content set and see that in the context of the wider knowledge graph. So while you couldn't build a knowledge graph with 400 or 4,000 or 4 million items, you could take those items and you can put them into a knowledge graph and you can identify them in the context of the other information. So hopefully that's helpful. I've got another question about, does the AI take into consideration existing taxonomies and metadata values? So the way our technology works, whenever we get an item of text, we do need the minimum metadata. So we would take whatever there was, and there are certain fields. So things like author, publisher, collection, if there is one, publication date, and so on and so forth. So things that I would class as traditional metadata, we do use those in our metadata schema. We use a version of mods. So we would create a mapping of those things to make sure that we've accurately got all of the kind of key parameters around the text. But we do not use the semantic metadata. So if, for example, a publisher, or a university has a collection and they provide keywords, again, we can't use keywords because the technology needs to read the surrounding text. So we would always read the full text rather than use some pre-prepared keywords. So I hope that answers the question, but if not, as I said, do feel free to write in and we're happy to try and address your question in a different way. So that is the end of all of the questions I've been sent on the chat. So I would just like to say thank you again to everybody for joining this morning. I hope it's been useful. If you do have any follow-on questions, do please feel free to email in and we'll try and answer them. And we'll also be sending everybody a copy of this recording tomorrow. So have a great rest of your day and thank you very much for joining.